is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing some more additional problems in radiation, the fourth unit of heat transfer. Here the problem is a gray surface has an emissivity at a temperature of 550 degree Kelvin source. If the surface is opaque, calculate its reflectivity for a black body coming from 550 degree Kelvin source. B bit. A small 25 mm square hole is made in the thin wall door of a furnace whose inside wall are at 900 degree Kelvin. If the emissivity of the wall is 0.72, calculate the rate at which the radiant energy escapes from the furnace through the hole to the room. Now the given data in the problem is the temperature of the body is given 550 degree Kelvin. If the surface is opaque, it is a condition is given. That means the transmissibility is equal to 0. That means from this relationship we got alpha plus rho is equal to 1. A small here given, a 25 mm size square is given. That means the area of this hole is equal to 25 into 25, which is equal to 625 mm square. The furnace inside wall temperature is given 920 degree Kelvin. The emissivity of the wall is 0.72. So the requirement that all the radiant energy striking any surface may be accounted for its relations. That is alpha plus rho plus 2 should be equal to 1 is required. Since it is opaque, the transmissibility is equal to 0, transmissivity, hence alpha plus rho should be equal to 1. This is the equations according to the opaque body. Now, here alpha is equal to here now, we got epsilon, that is emissivity, is given which is equal to 0.35 now. This is according to the Kirchhoff's law, which states that the absorptivity always equal to the emissivity under the same temperature conditions. So from this relation we got, that is here rho is equal to 1 minus alpha plus t. From this relationship we got 1 minus 0.35 plus 0, because transmissibility is equal to 0. From this relation we got 0.65 now. The surface reflects 65% of the incident energy coming from the source according to the relations. Here now reflectivity is equal to 0.65. B bit. The small hole acts as a black body. According to the rate at which the radiant energy leaves the hole is given by here E is equal to, that emissivity is equal to sigma B into A into T to the power of 4 now. So from this relation, sigma B is Boltzmann's constant, which is equal to 5.67 into 10 to the power of minus 8 into A, area of the hole, which is given now, that is 25. Here mm is given, that is divided by just 1000 in order to convert into meters, which is equal to 0.025 now. It is square value, area is equal to, if it is nothing but multiplication of side, again by side, and temperature is given 920 degree in Kelvin, so it is given to the power of 4 now. And doing the calculation we got, which is equal to 25.38 watts. So this is that is nothing but the energy, the small hole data is energy, from which the energy is limit it is given by 25.38 watts. The data about the emissivity of the inside value is not required according to the problem. Okay, another problem. The temperature of the flame in a surface is 1900 degree Kelvin. Find the monochromatic energy emission at 0.0 micron per meter square. Second one is delta maximum values. Third one is monochromatic energy emissions at delta maximum and at 1900 degree Kelvin. The ratio of EBY divided by EBY maximum, and finally we required E part, the total energy emitted per meter square. This values we have to determine according to these problems. Here the temperature of flame in a furnace is given 1900 degree Kelvin. Now the total energy is equal to emissivity is given by EBY, C1 into delta to the power of -5 divided by E to the power of C2 divided by delta T -1. Here in the relations now, here delta 1 is equal to emission is equal to 1 is given now, which is equal to 10 to the power of -6 meters, and EBY is equal to, on substituting the values in these equations we got, here C1 values, it is a given data, according to the relationship we got, C1 is equal to 3.7404 into 10 to the power of -16. Please just remember these values. According to the formula, the C1 is equal to 3.704 into 10 to the power of -16. Here delta is equal to, already we calculated, which is equal to 10 to the power of -6 to the power of -5 and divided by E. Again now C2 is equal to, again one more constant, which is equal to 0.014389. Please, it is also required to remember it, divided by 10 to the power of -6, that is equal to delta, into T is equal to absolute temperature, which is given 1900 Kelvin, -1. Then just you have to remember these equations to determine the total energy that is emitted now, which is equal to, on doing the calculations we got 1.91815 into 10 to the power of 11 watts per meter square per meter now. So according to the Wien's law is given, delta maximum is equal to, which is equal to 2900 divided by T, where T is representing the, that is absolute temperature of the furnace, which is equal to 1900, which is equal to 1.53 microns, or 1.53 into 10 to the power of -6 meter. Okay, monochromatic energy emissions, which is equal to EBY, that maximum is given. The same equations what we used earlier now. That is C1. C1 is equal to 3.7404 into 10 to the power of minus 16. Here 1.5 to 10 to the power of minus 6. That is equal to, here wavelength is given, to the power of minus 5 divided by E into here C2. C2 is equal to, already I told you have to remember, which is equal to 0.014389. It is a constant according to the equations, divided by 1.53 into 10 to the power of minus 6, which is equal to delta, the wavelength, into absolute temperature 1900 minus 1, which is equal to 3.183 into 10 to the power of 11 watts per meter square. The ratio of energy is given now. That is here now. Here EBY is given. The value is equal to 1.91815 into 10 to the power of 11 watts per meter square. Here it is given according to these equations now. EBY at the maximum is given 3.183 into 10 to the power of 11 watts per meter square per meter. So the ratio is nothing but, so when we are taking that value is equal to here 0.6048, that is the energy emitted at EBY to the energy emitted at maximum wavelength, which is equal to 0.6048. According to the Stefan-Boltzmann law, we got sigma EB is equal to sigma into 10 to the power of 4. Sigma is equal to Stefan-Boltzmann constant 5.678 into here T is equal to absolute temperature divided by here 100 to the power of 4 now. So from this relationship we got which is equal to 5.678 into 1900 divided by 100 to the power of 4. From this relationship we got 5.678 into 10 to the power of 4 into 1.9. From this relation we got 0.74 into 10 to the power of 6 watts per meter square. This is according to the Stefan-Boltzmann. The emissivity is given by 0.74 into 10 to the power of minus 6, 10 to the power of 6 watts per meter square. A black body of total area 0.05 meter square is completely enclosed in a space bounded by 5 centimeters thick walls. The walls have a surface area of 0.5 meter square and thermal conductivity is 1.07 parts per meter degree. If the inner surface of the enveloping wall is to be maintained at 215 degrees per centigrade and the outer wall surface is at 30 degrees centigrade, calculate the temperature of the black body. Neglect the difference between inner and outer surface areas of enveloping material. So the given data is total area is given, that is 0.05 meter square. Wall thickness is given, generally it is represented as a delta, which is equal to 0.05 centimeters. So wall surface area is equal to 0.5 meters. Here already given now, this values now. Meter square. Thermal conductivity is equal to K is equal to 1.07 watts per meter per degree. The inner temperature is given now 250 degrees centigrade. Outer wall temperature is given 30 degrees centigrade. So the net heat radiated by the black body to the enclosing wall is given by here QR, radiation is equal to sigma B into A into TB to the power of 4 minus TW to the power of 4 now. So sigma is equal to 5.67 into 10 to the power of minus 8 into here A is equal to area of the wall is equal to 0.045 TB is equal to, we have to determine minus 4.88 to the power of 4 now. Where TB is the temperature of the black body in degree Kelvin. Problem number 9. A furnace inside temperature of 2250 degree Kelvin has a glass circular viewing of 6 centimeters diameter. If the transmissivity of the glass is 0.08, make calculation of heat loss from the glass window due to radiations. A furnace temperature is given 2250 degree Kelvin. Diameter is given 6 centimeters. So, which is equal to 6 divided by, here given 100, which is equal to 0.06 meters. Okay, transmittivity of the glass is equal to 2 is equal to 0.08. The radiation heat loss from the glass window is given by Q equal to sigma B A into T to the power of 4 multiplied by 2. So, where 2 is representing transmissivity of the glass, which is equal to Q is equal to, here sigma B is equal to 5.67 into 10 to the power of minus 8. A is representing that is the area, surface area, which is equal to, viewing in this glass window which is in the form of circular is given, hence area is equal to pi by 4 d to the power of square now or 2 now. From this relation we got to pi by 4 into 0.06 whole square into 2 is given 2250 to the power of 4 and the transmissibility is equal to 0.08, which is equal to 328.253 watts. Here, I take one more problem. A polished metal pipe 5 cm outside diameter and 370 Kelvin temperature at the outer surface is exposed to ambient conditions at 295 Kelvin temperature. The emissivity of the surface is 0.2 and the convection coefficient of heat transfer is 11.35 watts per meter square per degree Kelvin. Calculate the heat transfer by radiations and natural convections per meter length of the pipe. Take thermal radiation constant. What would be the overall coefficient of heat transfer by the combined mode of convections and radiations? Pipe diameter is equal to D is equal to 5 centimeters. Temperature at the outer surface is equal to 370 degree Kelvin. Ambient temperature is equal to 295 degree Kelvin. The emissivity of the power is equal to, emissivity of the surface is equal to 0.2. Convection coefficient of heat transfer H is equal to 11.35 watts per meter square per degree. So, the surface area of the pipe per meter run is equal to the pi dl. So, surface area is equal to pi d perimeter multiplied by the length, which is equal to 0.157 meter square. QR radiation is equal to, here epsilon into sigma b into a into T1 to the power of 4 minus T2 to the power of 4. From this relationship we got here it is equal to 0.2 into sigma b is equal to 5.67 into 10 to the power of minus 8. This is the constant is given, where A is representing the surface area, which is equal to 0.157 and the temperature 370 to the power of 4 minus 295 to the power of 4, which is equal to 19.88 watts. Here QC is representing the convections according to the relations, which is equal to H into A into delta T, where H stands for the coefficient of heat transfer by convection, which is equal to 11.35. A is nothing but representing that is lateral surface area, which is equal to 0.157 into delta T is the temperature difference, which is equal to 370 minus 295. From this relationship we got which is equal to 133.64 watts now. So the total energy it is equal to, that is the total energy equal to 19.88 plus the energy due to the conventions, which is equal to 133.64, which is equal to 153.52 now. So the total heat exchange can be expressed as now total energy Qt is equal to Qa into delta T, where U is representing the overall heat coefficient and A is the surface area, delta T is representing the temperature difference, which is equal to, we required here now U value, which is equal to Qt divided by A into delta T. So 153.252 divided by 0.157 into 370 minus 295. From this relation we got to 13.204 watts per meter square per degree Kelvin. The problem number 12. A thin metal plate of 4 cm diameter is suspended in atmospheric air whose temperature is 290 degree Kelvin. The plate attains a temperature of 295 Kelvin when one of its face receives radiant energy from heat source at the rate of 2 watts. If heat transfer coefficient of both the surfaces of the plate is stated to be 87.5 watts per meter square per degree, work out the reflectivity of the plates now. The metal plate diameter is given now, that is 4 centimeters. Atmospheric air whose temperature is T1, we are calling 290. Final temperature is equal to 295. E is equal to 2 according to the problems. That is the heat source at the rate of 2 watts is given. Heat transfer coefficient is equal to 87.5 watts per meter square per year degree Kelvin. Heat loss by convection from both sides of the wall is given. Hence, both sides means you have to multiply by 2 now. HA, that is H is representing the convection heat transfer coefficient, which is equal to here now 87.5, and the A is represent surface area or area of the hole is equal to pi by 4 into d square. Here d is equal to, we are given now metal plate of circular 4 cm given, d is equal to 0.4 is given, 4 centimeters, which is equal to 0.04 meters. Hence pi by 4 into d square is equal to 0.4 whole square into the difference is equal to 295 minus 290. From this calculation we got to 1.1 watts. This is the heat transfer by convection process. For the solids, for the most of the solid, the transmissivity is equal to 0. Hence, heat loss by the reflection is equal to, because the total is given here 2 now, the heat transfer by the conduction process is given 1.1. So, through reflection is equal to, we are having just a total energy is equal to given now. It is equal to the sum of the energy transmitted through conductions and transmissions, one more reflectivity. By using the relationship we got to heat lost by the reflection is equal to total reflections minus 1.1 conductions, which is equal to 0.9 watts. So reflectivity is defined as the ratio of heat transfer by the reflection to the total energy, which is equal to 0.9 by 2.0, which is equal to 0.45. Okay, thank you.
like, share and subscribe. Hit the bell icon for more updates.